So in this video, we'll look at the second version of the comparison test. If you have watched the previous video on the first version of the comparison test, it is essentially an limit version, but sometimes we require other versions of comparison test. And let's look at the current case. We still require all the terms in the two series to be positive. All terms are positive. That's the first requirement. If it happens like that, and if all the terms in the first series is actually less than the terms in the second series for all n, an is less than or equal to bn, and of course if you sum up all these terms together one by one, the first series is still less than or equal to the second series, right? And the fact is that if the bigger one is actually convergent, it means that when you keep adding the terms for the bigger terms, it's actually approaching a fixed value. And I claim that in that case, the smaller series, which is the infinite series containing the smaller terms, is also approaching a fixed number. It is convergent. And it is one version of the comparison test. And the second one is that if it happens that the first term an is always bigger than or equal to the second term, and when you sum up all the terms, obviously the sum of the first series is at least the same as the second series, right? And let's say the smaller series is actually divergent. Please record that all the terms in the second infinite series are positive, right? At least non-negative. So when you keep adding so many terms and it is divergent, essentially means it is going to infinity. So you can try to imagine what's happening for the smaller infinite series when it keeps going to infinity. If of course we expect that for the bigger series with the bigger terms, it's also go to positive infinity, right? Because it is in terms of size at least equal to this sum. So I think it makes sense that the bigger series also is divergent. And let's look at some examples together. So please look at the current problem. You see the problem about this is that if you try to use the comparison test, which is possible, but the fact is the first version of the comparison test described in the last video cannot be applied here because you cannot take limits for the sine function. Because the fact is that you see, for the sine function, as everybody have learned, it's like water wave functions. It is always alternating between 1 and -1 when you keep going to the right-hand side. So there's no fixed limit when n goes to infinity, right, for the function sine of n. Because you cannot determine the limit of this, and there's no chance we can apply the limit version of the comparison test. But still, sine n is still a nicely behaved function in the sense that we understand that sine of n is actually bounded between -1 and 1 for all n, for all. So why is it useful? Because we try to compare our original series with something easier by using the fact that sine n is actually bounded inside -1 and 1. And let's see how to do it. The terms that we have now, you see, of course, should be positive all time because this one is at least -1, right? In that case, the numerator is positive because at least you get something like 2 plus -1. So I can write it down here. For this term itself, it is actually bounded above by 2 plus 1 divided by 3 to the power n, and the lower bound is actually 2 plus -1 divided by 3 to the power n. Essentially, I'm just using this inequality, right? And of course, you can sum up all these terms one by one for all n. So I write it down here. So please look at the current inequality now. I claim that the important part for us is this, because we can see that we can actually determine what happens to this infinite series. And let's unravel the terms together. We can even cancel one power of the 3, so it becomes 1 over 3 to the power n minus 1 inside the infinite series. And now I trust that you're able to tell me what's happening to this series, because this one is actually a series like this. If you write all the terms down, and it's actually quite obvious that it's actually a geometric series in the sense that the fixed ratio, which is the multiplicative ratio you use to get to the next term, is actually 1 over 3, right, as a fixed ratio. And by the geometric series test, because it is less than 1, we understand that it is a convergent geometric series. And let's come back to our purple box here. And because you see all terms are positive, there's no doubt about it. And the upper term is always bigger than the middle term here, and the infinite series formed by the bigger term, we know that it is convergent, right? And based on my last page on the criterion for applying the second version of the comparison test, we understand that the smaller series with the smaller terms is also convergent, right? So I write down the final answer here. It is convergent because our current series is less than the bigger series, which is itself convergent, right? And that's the answer to this problem. We can look at one more problem now. Please look at the current problem, and as a good habit, if you want to check whether the previous method you learned can be used to attack this problem, the answer is yes. Actually, the fact is that you can actually use an integral test to do an integration for ln x over x for 1 up to infinity. You can do this integration, and after the integral test, you can get the answer quite quickly. It is a u substitution integration. You can let u be ln x. So you can go and try yourself. We are not going to do integral test here. Let's see how to apply the comparison test. The fact is, this one, of course, it is not a p-series because of the fact that you see the top is not the constant. The top itself is somehow a little bit annoying because it keeps increasing itself, which is a ln n term. But the fact is that the ln n is an increasing function all the time. You see, it's y equals ln x like this. So if you look at this x-intercept, it is x equals 1. If you look at 2 here, it is ln of 2. If you look at 3 here, it is ln of 3, and so forth. So ln of 3, ln of 4, ln of 5, etc. It keeps increasing. And it means that I can think of it like this. Please look at my expansion. I think the first term here doesn't matter because it is 0, right? Because ln 1 is 0. That's it. So we can forget about the first term. We can start determining it from the second term. You see, the fact is that if you just look at this value, ln of 2, ln of 3, ln of 4, this one itself keeps increasing, numerically speaking. So it means we can think of this infinite series as bigger than the series if I replace the top by ln of 2, right? Because I can do this replacement because I want to bring down the values of the second term and so on. If I'm doing it, it is valid because now the top is always ln of 2, which is a smaller fraction comparing to each fraction you have here, right? And let me write it in a slightly better way. So you see our current series, because I'm trying to use a comparison test, and ln n is quite an annoying function at the top of the fraction, but because it is an increasing function, I would like to bring it down the values of each term. So our current series is actually bigger than the newly constructed infinite series. And ln of 2 is a constant as a common factor for each term inside the infinite series, so I can bring it out, right? And this one, I trust that you know the answer because it is related to the harmonic series and by the p-series test, because now the fixed power, the p is 1. Whenever it is 1 or less, we understand that by the p-series test, the answer is actually divergent when the p is 1. And it means what? Please look at the whole problem. First, all these terms are positive, all these are positive. So that's the first condition which is satisfied in the comparison test. Second, the smaller series with the smaller terms here. This is divergent based on the use of the p-series test. You see, when the smaller series is going to infinity, of course, we expect that the bigger infinite series with all these bigger terms is also goes to infinity, right? So by comparison test, we actually get the answer pretty easily. So let me write it down here. So by comparison test, the current series we consider is actually divergent based on this fact. And that's the end to this video.